Okay, just give a minute for more people to log in. It's kind of like, when you have seminars in person, there's always people coming in late. Although I think sometimes the best thing we do when we have speakers in person is just the chit chat time before the talk and after the talk. We get to know a lot.
Yeah, I'm happy to stick around, by the way, afterwards. I mean,
Okay.
I don't have any commitment after my talk, so I can take questions. We can chat a little bit, no problem.
Okay. All right. Well, welcome everybody. We'll get started. Today's speaker is going to be talking about ultra high energy cosmic rays. Professor Meyer and I used to work with Professor Fred Sarrazin at the University Colorado School of Mines. And Fred is a professor there and a distinguished scientist in cosmic ray science. And he's been doing a lot of this from the early days of what we call the Pierre Auger project. And he's now extending it to some space-borne projects and multi-messenger astrophysics. And he's going to talk today. So please welcome Fred.
Okay, hello everybody. So thank you for the invite, Nick. It's a pleasure really to be back, quote unquote, at Wichita State. I've had fond memories working with you and Olger on the R&D project that we had together in southeastern Colorado. So it's good to see you again. Okay, so I will be talking about ultra high energy cosmic rays, and I'll review some of the results from the largest ultra high energy cosmic ray experiments, which is based in Argentina, called the Pierre Auger Observatory. And then after that, that's going to be most of my time. And then after that, I'm going to show you that there is a path to actually study ultra high energy cosmic rays from space. And there is kind of an incremental step in which you don't go directly to space because it's very expensive. So what you do is you start planning on balloon experiments, but as I'm going to tell you, balloon experiments needs to stay in flight for much longer than a typical balloon experiment that might last 1 or 2 days. Here we're aiming for something like 100 days. So I'll tell you all about this. Okay. So this is going to be the outline of my talk. I'm going to be talking first about what are ultra high energy cosmic rays, UHECRs. And then I'll tell you about the Pierre Auger Observatory. And, there are lots of results coming from this experiment. It's a very mature experiment now that is about 15 years old, over 15 years old, actually. And I have to select a little bit of the results. And one thing that I'm not going to talk very much about is that this observatory is actually undergoing an upgrade at the moment. And so we are probably going to be operating until about 2030 at the, and might be beyond. So we've got another 9 years of operation also. And then I'll tell you about a path to a ultra high energy cosmic ray space observatory. All right, so let's start with a description of the cosmic messenger. So this is something that you probably have heard already. Most of what we know about our universe actually comes from the observation of photons. And by photons here, I'm very broad. I'm talking about the whole electromagnetic spectrum from radio on the one end to gamma rays on the other, and very high energy gamma rays, and anything in between that, of course, includes optics, X-rays, microwave, and so on. Now, we know that, and we've known for a long time that there are some other cosmic messenger. The problem is that they were very tricky to detect. And historically, I think that the next one that was actually detected are cosmic rays, which is the one at the bottom here. And cosmic rays are charged particles. We know we're being bombarded by charged particles, but the problem of charged particles, of course, is that they're bending in the magnetic field of our own galaxy. And so it's not obvious at all that if you're measuring the arrival direction of a cosmic rays coming and impinging on our atmosphere, right, we're going to be pointing back to the direction of a source. In fact, this is very unlikely to happen until you're at a very, very high energy where the deflection in the magnetic field is somewhat minimum here. And this might be happening of the order of 10 to the 20 electron volt, which is the highest energy cosmic rays that have ever been detected. And this is what I'm going to be talking about in this talk. Now, I want to mention the other messenger because those are very important as well. And in the past, 5 years, it's been, the progress on this has been tremendous. First one is neutrinos, and we know already that neutrinos are coming from the sun because of the fusion reaction occurring in the sun. We do have a production of neutrinos, so we know neutrinos are coming from the sun. We know also that neutrinos are emitted during supernovas. We've been detecting a burst of neutrino out of 1987A with a detector called Kamiokande. And as of recently, we've also been able to detect high energy neutrinos, and this was done by the IceCube experiment from an object called a blazar, which is a quasar with basically a jet that is pointing towards us. And so the object is called TXS 0506 plus 056, also known as the Texas blazar. And this was observed in multi-messenger mode, which means that we were detecting those neutrinos, a few neutrinos, but really only one directly with high energy photons when the blazar was flaring. So this gives you an indication that neutrinos could become a cosmic messenger, and neutrinos are great, right? If you think about it, because they are not charged and their cross-section with matter is extremely small, so they're going to be traveling in straight line. So if you measure a neutrino, you can be pretty sure that it's going to be pointing towards a source, right? The problem is that detection, even on Earth, is very challenging. And now the big newcomer about 5 to 6 years ago was the discovery of gravitational wave and their first measurements. And this incredible event that happened in 2017 when we saw a neutron star merger, where we were able to not only pin down where the neutron star merger appear by kind of triangulating the observation of gravitational wave from 3 gravitational wave detectors, but also the follow-up in visible in optical wavelength, infrared, X-rays, and so on. And so this has been like a tremendous source of information about what happens when 2 neutron stars are merging together. So I'm going to leave a lot of those cosmic messenger. I'm going to talk mostly about cosmic rays, but I'll mention again neutrinos towards the end of my talk. Okay, so we have measured now the neutrino, the cosmic ray energy spectrum with, in a quite detailed fashion from the lowest energy, the ones that are coming from the sun, all the way to the highest energy, which are the ones that I'm going to focus on, which are the ones that are located in kind of this region here. This flux here is actually corrected by an energy factor here. So what you have to imagine is that this is a power flux, power law flux that is basically dropping about 2 to 3 orders of magnitude in flux for every decade of energy that you increase the energy. And so when you get to this region here that I'm pointing out here, the flux now of ultra energy cosmic rays is less than 1 particle impinging our atmosphere per kilometer square per century, right? So the flux is extremely low. And so the first thing that you can imagine is that if you want to study those ultra energy cosmic rays, you're going to have a very, very large detector to compensate for this very, very low flux. And so we'll be talking about that. There are some other feature of the spectrum, such as the knee and the ankle, and the break in those power laws is basically something that allows you to kind of guess that there is something going on here. And basically, it's widely believed that somewhere between the knee and the ankle, or around the ankle, you have a transition between galactic and extragalactic cosmic rays. So what that means is that at the highest energy here, the source of those ultra energy cosmic rays probably don't come from our own galaxy. And in fact, with Auger, we've been able to prove that. And I'll show you that in a minute. Okay, so if you want to do charged particle astronomy, which would be, figuring out what is the origin of those ultra energy cosmic rays, you have to be in a regime where you measure the arrival direction of ultra energy cosmic ray impinging on atmosphere, and then reconstruct its arrival direction and point back to a source. Now, the problem is that the universe is really, really big, and considering that those cosmic rays are basically charged particles, that you're not going to get a very, very accurate reconstruction of where that cosmic ray came from. Even if you reconstruct within 1 or 2 degrees their arrival direction on Earth, that those cosmic rays probably got deflected while they were traveling towards Earth, right? And so the problem is that if your angular resolution to do astronomy is not very good, then potentially you have a problem, because the universe being so big, if you point in any one direction of the sky, you are going to find sources, right? And so how do you, distinguish the source that could be coming from cosmic rays? Well, one thing you can do, of course, is look at the astrophysics of those sources, because, you have to be able to come up with an accelerator, an astrophysical accelerator that is going to produce particles at 10 to the 20 electron volt. Not everything is able to do that. But in a sense, we got a little lucky, because shortly after the discovery of the cosmic microwave background, there was a paper that was written by Kenneth Greisen in the US, but also Tsetsepin and Kuzmin in the Soviet Union, that basically explained that for ultra energy cosmic rays, let's say a proton that is traveling in the field of the cosmic microwave background photons, right? In the reference frame of this proton, the cosmic microwave background photon may appear sometime very, very blue shifted, especially one that is coming towards the proton. And, the cosmic microwave background photons has an energy of the order of 10 to the minus 3 electron volts. But actually, because of the boost in the reference frame of the ultra energy cosmic rays, that energy turns out to be hundreds of MeVs. And hundreds of MeVs means that you can actually excite the proton into a delta resonance and induce some energy loss processes. So that means that if you detect something that is very, very high in energy, right, and it remains at very high energy all the way to Earth, that means that it has not interacted too often with those cosmic microwave photons. And so from that, you could say, well, they had to come from reasonably close by. And by reasonably close by here, we're talking about, anywhere between 10 to 100 megaparsec. So a parsec is about 3.3 light years roughly. So we're talking about the nearby universe, about 330 million light years. And you might think, well, that's still really far away. But if you think about the size of our known universe and you consider a volume, right, this so-called Greisen-Tsetsepin-Kuzmin sphere, the so-called GZK sphere, is actually really quite small. By the way, the effect itself of the interaction of cosmic microwave photons onto ultra energy cosmic rays is called the GZK effect. And so it induces a GZK cutoff on the spectrum of cosmic rays, and also a GZK sphere that I'm mentioning. So here's the good news, right? We don't have to deal with the sources that are really, really far away. The sources have to be nearby. And that means that, we can kind of afford to have, let's say, a lesser angular resolution in our detection and still be able to infer the sources that may have produced those ultra energy cosmic rays. Okay, so talking about accelerators now, well, you have different, you can come up with different sources depending on the acceleration process. So generally speaking, not going too much into the detail here, but generally speaking, what you need for an acceleration is you need to have an acceleration process, which is typically some kind of shock acceleration. But you have to be able to keep the particle being accelerated in the source for as long as you can in order to have it going through that shock many, many times in order to get accelerated to the highest energy. And so on this plot here called the Hillas plot, you have the size of the source and the magnetic field strength. And so you can think about objects like a neutron star, for example, that is very, very small, but has a very, very large magnetic field. And so you can confine the particles and accelerate them to those energies. On the other end of the spectrum, you can think about, some objects that are very elongated, right? So such as radial lobe of galaxies, for example, right? And in this case, you don't necessarily need a very, very large magnetic field in order to confine those particles and accelerate them to the proper energy. So let me give you an example of what that does here. So in the southern hemisphere, there is a galaxy called Centaurus A, which is part of a class of galaxies called active galactic nuclei. And what it is basically you have the galaxy here that is sitting somewhere here. And right at the center here, you have a supermassive black hole that is powering a jet that is accelerating particles basically perpendicular to the jets, creating what are called, eventually forming what are called radial lobes, which are actually really big. In fact, they are much bigger than a galaxy. And so this picture here basically represents NA if you were to be able to see it with the naked eye. So this is an object that, despite the fact that I think it's something like 20 or 30 megaparsec away from Earth, is something that would look really, really big if we could see it, compare that to the size of the moon, for example. So here's the problem there. Again, if you want to do charged particle astronomy, if the source of the cosmic rays is the supermassive black hole right at the center here, which would be basically the core of this AGN, so those are called AGNs, right? Then what you can do here is you can think that, well, this object is actually not that big. And so you can kind of imagine that if you were to do everything right, you might be able to reconstruct the arrival direction. But what if this actually come from, the emission of those ultra energy cosmic rays come from those radial lobes here. Now you have objects that have 20, 30 degrees that are looking like have an angular opening of 20, 30 degrees in the sky. And then doing charged particle astronomy becomes really, really complicated if you add all the other problems that you might have. Okay, so that's a little bit of a cautionary tale here of how we can do charged particle astronomy even if everything goes right. Okay, so now let's talk about how do we detect those ultra energy cosmic rays. Well, we cannot exactly put a detector in space and basically detect them and stop them. There are two reasons for this. First, the flux is very low, so remember you need a very large detector. But the second is that at those very, very high energies, you cannot stop that ultra energy cosmic ray. It's going to basically interact and produce a shower of particles. And at the maximum development of such a cosmic ray shower, you may have something like 10 billion particles that are going to be produced. And so what we're going to do here is we're going to use the atmosphere as our detector. And therefore, when ultra energy cosmic ray particle is going to start hitting the upper atmosphere, it's going to produce this shower of particles. And some of them are basically going to eventually hit the ground there. And so we're going to be detecting, a sample of those particles that have hit the ground. And we're going to reconstruct the properties of the shower, including its energy and arrival direction, to reconstruct basically the property of the ultra energy cosmic ray that has been detected. Okay, so how do we do this? Well, that's why the Pierre Auger Observatory was built. So it's an array that is made of 1,660 detector stations, which are made of water tanks. Their spacing is 1.5 kilometers apart. And so the entire surface area covered by this detector here is of the order of 3,000 square kilometers. So I'll give you a sense of what this represents in a minute. And then at the surrounding of this array here, we have what are called fluorescence detector. And those fluorescence detector are basically optical telescope, well, not optical, they are UV telescope that allows to measure the development of a cosmic ray shower in the night sky as it travels through the atmosphere. So I'll give you a little bit more detail about all those in just a second. So just to give you an idea of what 3,000 square kilometers look like, I've basically superimposed here the outline of the observatory over the Denver metropolitan area here, and you see that it's pretty big. It's about the size of the state of Rhode Island. The state of Rhode Island is about 3,140 square kilometers, so it's actually pretty close to the surface area of this detector. This is the largest detector in the world in that respect. Okay, so let me recap here. So the way the Pierre Auger Observatory works is that we have detector on the ground, which are going to measure the density of particles that are hitting the ground. So we're going to be sampling the density of particle in the shower. And then we have so-called fluorescence detector here that are going to be looking, they're going to operate like, like optical telescope. They're going to be looking at the light that is being emitted as the shower of particle develops in the atmosphere. And the reason why this happens is that all the particles that are being produced, especially electrons that are produced in the atmosphere, they're going to excite the nitrogen molecule and induce the nitrogen molecule to fluoresce. And so the fluorescence process produces UV light, and that UV light is emitted isotropically. And so those detectors basically are going to measure a fraction of that and allows for the detection and following up the development of the shower as it's traveling towards the ground. So the observatory actually has the two types of detector. And so one thing that I'm going to mention a little later is that it's a hybrid detector because it's using the two methods of detection. Okay, so just to show you what those detectors look like. The surface detector, like I told you, it's basically a tank of water, and I'll explain how it works in just a second. And then those buildings here, they're basically hosting those telescopes that are detecting the UV light. Okay, so going into a little bit more detail here, the fluorescence detector, we call it the FDs, and the surface detector, those are the SDs. They are basically, they are basically measuring different properties of the shower. So the FD is measuring the so-called longitudinal profile of the shower as it develops from the upper atmosphere down to the ground. So you see that you start producing more particles. So all those particles interact with the upper atmosphere, produce more and more light. Eventually you reach kind of a maximum, and then the light basically dies down because some particles are being absorbed in the atmosphere, and so you have less and less particles that eventually hit the ground. So that's actually a calorimetric method, which means that somehow if you take the integral of that and you add a few corrections, you can actually get the energy of the shower. So that's very powerful. Now here is the downside to this is that the duty factor of this of the fluorescence detector is only about 14%, because you can only operate those detectors at night, and the atmospheric condition needs to be very good. So that amounts to about a 14% duty factor. Opposite to that, the surface detector, which are all the detectors that are located on the ground, have a duty factor of about 100%. And like I said, they're measuring the lateral distribution function of the shower. So at the core of the shower, you have a lot of particles that would be there like this. And as you move away from the center of the shower, you're detecting less and less particles. And eventually, all the particles that you detect very far away from the core are basically mostly muons. So it's a type of particle that are basically not stopped very, very easily, as opposed to electrons, for example. So we can use that as well. I'll tell you a little bit about this. So here is a picture of a fluorescence detector building overlooking the Argentinian Pampa. So this is the building here. So this is a picture of the actual telescope. So you have the entrance aperture here. So your UV photons are going to be coming like that. You have a mirror that is going to reflect those UV photons to the focal surface here. And the focal surface is made out of 440 PMTs per telescope. Every telescope has a field of view of about 30 degrees, so you need quite a few in order to cover 180 degrees. And basically, it's like a digital camera, except that you're able to take a picture every 100 nanosecond or so. So, like I said, the information that you get out of that is this longitudinal distribution of the shower. But then you can also reconstruct, its arrival direction because, well, on the camera, you're going to see the shower developing in a plane called the shower detector plane. And then, of course, you have also the timing of arrival of all those photons that gives you the third dimension. So from that, you can actually reconstruct the arrival directions of those cosmic ray showers. Now, like I said before, basically the way the fluorescence detector is operating is that it's overlooking the surface detector array. So for most of those, 99% of all those events, you are going to see a signal on the ground, which actually allows you to pin down even better the geometry. So that's how powerful the hybrid technique is. Now that's the surface detector. So the surface detector is made out of those water tanks here. And so if I'm showing you what this looks like here, there's a little bit of a delay here. Here we go. Oops. So this is about, the detector are about 1.5 kilometers apart from one another. Like I said, it's a water tank and you're measuring the shower density. And so the way it works here, you have a shower particle that comes in. It's actually traveling faster than the speed of light in water. And so it's going to start decelerating by emitting Cherenkov radiation. That Cherenkov radiation in water is going to be reflected into the liner, being collected by a photomultiplier tube. And out of that, you're going to get a signal. And then, the intensity of the signal gives you an indication about the shower, the particle density, where, your tank is basically located. So out of that, like I told you, you reconstruct the lateral distribution function of the shower here. And then what you need is basically an observable that you're going to be able to relate to the energy of the shower. And so I'm not going to go into detail here because it's a little complicated, but you have to account for a few, some geometry and interaction in the atmosphere. But basically, you can come up with a measurements that is effectively universal for all the lateral distribution function that you're going to measure. And this quantity called S38 can then be, so let's say this is S38 here. This quantity S38 can be plotted as a function of the fluorescence detector energies for all those hybrid events, right? And out of that here, you get basically a calibration, right? Which allows you afterwards to calibrate the surface detector so that if, for example, you detect an event with the surface detector during the day, you don't need the fluorescence detector information. You basically use this calibration curve here to assign its energy. It's very, very powerful, and it works actually extremely well. The other curve that you see here is that for different type of showers, we've got different calibration curve. I could give you a lot more detail on this, as you can imagine. So here is a beautiful event here that basically landed roughly in the middle of the Auger array and was actually seen by all 4 FD buildings at the same time. And I just want to remind you again, the distance between those dots here, right, is 1.5 kilometers. So if you think about the distance between here and here, it's probably upward of more than 20 kilometers or so. So you basically can observe a cosmic ray shower 20 kilometers away just by the light that it's producing in the atmosphere. I mean, we're talking about a lot of energy here. And 10 to the 20 electron volt, right, is something of the order of a joule or so, a few joule of energy that is being dissipated. Okay, I'm not going to spend any time on this slide, but this slide is actually really important. Remember that we're using the atmosphere as our detector, and therefore the first rule of experimental physics is know your detector. So we have a lot of atmospheric monitoring devices that we're using in order to understand our atmosphere at the time of the measurements, so we can do all sorts of correction for the light attenuation and so on, which is possible due to, for example, aerosol scatterings and things like that. Okay, so let's talk about the results now. After about 15 years of operation, we've got a very, very good handle on the cosmic ray spectrum. And we've recently published, just last year, our latest results on the cosmic ray spectrum. And so what you see here is features that we knew already, like the anchor, for example. The flux suppression here, which is, so this is one that is a little tricky here. It's happening around the energy that is expected due to the GZK cutoff, if, for example, protons were to be the primary particle. So there is a flux suppression here, but as I'm going to tell you later, it's really not obvious. In fact, it's unlikely that it's related to the actual GZK process that had been predicted in the 1960s. Now, there is a new feature here that is basically fairly unexplained here, which is kind of a flattening of the spectrum, at least for in between a certain energy. And I'll tell you in a minute what it probably means. But this is one that is actually pretty hard to understand. Once again, I want to point out that this is a spectrum that is corrected in e to the power 3, which means that it's not what the spectrum really looks like. What the spectrum really looks like is that this is corrected by e to the power of 2, and you see that the spectrum is continuously going down, right? So it's not like there is the flux start to go up in a certain region here. The flux is continuously going down very, very steeply. But in order to be able to highlight those features, we basically put a large energy correction factor in order to be able to see those features better. But in fact, you have to imagine that the flux is very, very steep. And if I was to show you the flux without correction, you would barely see the change of slope due to all those features. Okay, something else that is worth mentioning is that you can basically, the observatory is looking at quite a big region in the sky. It's not be able to see all of the northern hemisphere, obviously, but it's seeing all of the southern hemisphere, plus because of the inclination of the tilt of the Earth, right? You get to see sometimes some other region of the sky. So you can see basically up to about 30 degrees in northern latitude, roughly speaking. And so you can basically make some cuts in declination bands. And if you do that, you see that the spectrum actually remains the same, which means that there is no one source somewhere in the sky that is responsible for the emission of those ultra energy cosmic rays. That makes our job a lot harder, because what it means really is that there's probably not a dominating source in the night sky, well, in the sky for the emission of ultra energy cosmic rays. Just as an aside here, there is an experiment in Utah called Telescope Array, which is about 4 or 5 times smaller than Auger, that is also studying ultra energy cosmic rays. And at the moment, there is a little bit of a tension between the two spectra, the one observed by the one measured by the Pierre Observatory and one measured by the Telescope Array. Now, because of the energy systematics between those two experiments, you can actually get those spectra to line up. But around this energy here, you would still see quite a bit of a difference in terms of the flux at the highest energy. And so you could think about this like, well, if the flux is higher in the northern hemisphere, maybe there is another source of ultra energy cosmic rays that would be responsible for this extra emission. Turns out that at the moment, that source has not been identified. So one other thing that it could be is basically a difference of bias in terms of detection or reconstruction that are not very well understood between the two experiments. And this is something that I'm strongly involved by. Basically, I'm going to work with a group of scientists to deploy a micro array of Auger detector in Telescope Array to do some kind of cross calibration to try to understand whether this discrepancy is actually due to experimental artifacts. So I don't have very much time to talk about this. Okay, so going back to charged particle astronomy, because that's really, the goal of the Pierre-Auger Observatory is to find the origin of ultra-energy cosmic rays. Well, something that that finally came out of making, very prolonged measurements is that we're able now to reject the fact that those ultra-energy cosmic rays are coming from the galactic center. And we can do that by looking at the flux, the arrival direction and the flux of cosmic rays coming from particular region of the sky. And so this here, of course, is the region that we cannot access. So this is in galactic coordinates. The galactic center is right in the middle, and you see that it's in the blue region here. And the blue region has basically a smaller flux than like a hotter region of the sky, which you see as some kind of dipolar nature to this, right? So this is rejecting fairly conclusively that the ultra-energy cosmic rays, and it was somewhat expected, are not coming from our own galaxy. Our galaxy, especially even at the galactic center or the supermassive black hole that we've got in our galaxy, is not particularly active. There is no obvious source of acceleration there. So it's something that was somewhat expected, but now we've been able to basically discover that in a sense that we've got a signal that is greater than 5 sigma. And in fact, with 15% more statistics since the publication there, we're now over 6 sigma significance on this. Now, interestingly, the center of this dipole here is located in a region that is roughly around here. And if you look at a catalog of source distribution in our nearby universe here called the 2MRS catalog, the center distribution of mass should be somewhere around here. But now if you account for the effect potentially of magnetic field here, you actually see that the magnetic field will tend to deflect the particle in this particular direction, which makes basically the center of that dipole pretty much right around you would expect. And so that's also very significant. But if you think about that, that's the bad news to do small scale anisotropy because of the large deflection that are involved. Now, this is at 2 to 5 EeV. So 5 EeV is 5 × 10⁻¹8 electron volt. Remember that what we would like is we would like to look at 10⁻20 electron volt when the particle might be traveling in straighter line, if you want. So one thing we can do then is we can make cuts at higher energy and see if we are getting closer to a correlation at smaller scale. And so we've done that. And we started with a blind search here, and we found that there is indeed a region that is a little smaller here, where the flux of cosmic rays seem to be the highest. And we can test that against a different catalog. And the two that we like in terms of, the type of objects that could produce those ultra-energy cosmic rays are active galactic nuclei and starburst galaxies. In both cases, those galaxies are basically producing shock, which means that they can produce also shock acceleration, and which would fit within the acceleration of very high energy or ultra energy cosmic rays. Now, here is the problem that we have. This is Cna here. This is the active galactic nuclei galaxy here that I mentioned before. And here is basically a close by starburst galaxy. And it turns out that they are very, very close to one another. So if one of them is a source, be able to distinguish between the two of them is actually really, really hard. And in fact, the difference between the search, the significance of the search to find out which object might be more favored to be a source for ultra-energy cosmic rays very much come from this object here, where you see that in this kind of south pole on this map here, you have also an excess production of ultra-energy cosmic rays, which actually relates to the presence of a starburst object, whereas you don't have such an object for AGNs, right? But you see, this is not necessarily something that is a very, very strong signal yet. So we have to wait until this signal grows bigger or more significant. All right, so I'm running behind here, but I really want to mention this because this is really important. So there is this question, which I started from, which to say, well, if the ultra energy cosmic rays are protons, then because they are only charged one, they would be traveling in a relatively straight line, and we should be able to see small scale anisotropy. And everything that I've showed you so far seems to indicate that it's not. So the question is, well, do we really know whether what is coming, the ultra energy cosmic rays that are coming, are protons? And originally, before the Pierre Auger Observatory was built, a lot of people thought that protons would be the only particle that would basically survive the acceleration process at those energies. Well, we can measure not on an event basis, but by groups of energy, we can measure the average mass of the primaries based on the way they interact in the atmosphere. And so the story, the way it works is the following, right? If you have a proton, for example, coming in the upper atmosphere, its chance probability of interacting makes it that sometime it's going to be able to interact deeper in the atmosphere. And so they are going to be, the average, if you have a group of protons that are going to interact in the atmosphere, we should be able to measure the maximum interaction in the atmosphere to be slightly deeper, for example, than if you had ion nuclei, right? Because ion nuclei have a higher probability of interacting early on. And that's simply because, ion is made of 56 times more, 56 nucleons compared to proton only one. But you see also that there is something called a shower-to-shower fluctuation, which is a lot narrower for ion than it is for proton. And so if you're measuring some of the properties of the shower, which is done by measuring the properties of the longitudinal profile of the shower, you are going to be able to get a sense of how heavy the primary is. Okay, so we've been able to do that, and this is what we're measuring here. So this needs to be weighted by hadronic models. So we need to be able to get some kind of reference that is provided by hadronic models. But basically what you have here is the evolution of the mean of X max as a function of the energy. And you see that the shape here, because, at the beginning is kind of away from being pure protons. Then you get towards a point there around here where you have mostly pure protons. But then, and somewhat surprisingly, right, the evolution of this is moving towards heavier particle. And so if it becomes heavier, that means that the primaries have a larger Z. That means that because they have a larger Z, they're going to be more deflected in the magnetic field of our own galaxies. And the very strong signal that you would expect in small scale anisotropy would start now being washed out. And that's pretty much what we see. And so this picture here is this another variable here, which is the shower-to-shower fluctuation. And you see at the beginning, you observe a lot of shower-to-shower fluctuation, which is consistent with protons. But then you start to get a lot less shower-to-shower fluctuation, which, remember, is a sign of having ion, right? The shower-to-shower fluctuation here is a much smaller. So it's a lot more predictable. Okay, so this indication really goes along everything that we've seen, which is that, we are not able to see small-scale anisotropy. We're not able to see individual sources the way you might be able to do with, optical telescope, for example. So that was a little disappointing. I'm going to skip this one here. You can do a similar work with the surface detector, but it's a lot harder. But the advantage of going with the surface detector, of course, is that because you have a 100% duty factor, you have more statistics at the highest energy. So in principle, you can push this analysis further. But that's a very, very complicated one. Okay, let me open a parenthesis here. This is not the only thing that the Pierre Auger Observatory can do. It's not only detecting ultra-energy cosmic rays. In fact, it can detect ultra-energy photons, and it can detect ultra-energy neutrinos. Now, the chance probability of that is a lot lower, of course, because detecting a neutrino interacting in our upper atmosphere is pretty small. But at the same time, it would have it would be really, really important to detect some of those. And so far, the only thing I can tell you is that we haven't found the neutrino candidate yet that has been detected. Detecting ultra high energy neutrinos would be really important to figure out, for example, how many protons we may think we have at the highest energy. Okay, in terms of multi-messenger, I also wanted to mention that when the neutron star merger happened, there was a search of neutrinos, and because Auger is a neutrino detector, there was a chance also that it would detect neutrinos, and Auger was not, it was able to put basically a lower limit on the emission of neutrinos at the highest energy. And similar for the Texas blazar here. This is a picture taken from IceCube, and in the interest of time, I think I'll skip this one, but basically the calculation for Auger was that we did not expect a cosmogenic neutrino visible given the flux that was detected by the IceCube experiment. Okay, so going back very quickly to the spectrum here. At the end of the day, based on everything that we've learned so far, we are facing a little bit of an issue in a sense, is that everything that we've, the way the observatory was built originally was really to be detecting proton at the highest energy. Well, the fact that we don't necessarily detect proton at the highest energy might mean that those protons may just not be there. Right? And in this case, you go from what is called the photodisintegration scenario here to the maximum rigidity scenario, where basically the source basically run out of steam. And so they're going to be producing proton, but only up to a certain energy here. And then, helium would be accelerated and they would also die out eventually. So helium would stay longer in the source. They would be able to be accelerated to a higher energy because their charge is 2 instead of 1, right? And so you can imagine that then, the kind of a nitrogen group would be accelerated and eventually will die out. And then towards the end, you would have iron that would be accelerated and then would die out, right? In this case, it's the termination of the cosmic ray spectrum is basically due to the fact that the source ran out of steam. And it's not because they're able to accelerate proton to those gigantic energies. And so the latest analysis that was done here, considering all the data that we've got, which correspond to composition and the spectrum, if you try to fit all of the data at once in the model, basically you seem to be favoring the fact that it's the second scenarios I mentioned, so the source end up running out of steam. The thing though is that so far we haven't seen really that ion contribution yet. We're seeing that, it seems that as we go higher in energy, you see that the contribution that dominates is heavier and heavier, but we haven't been able to reject the fact that there are no protons at the highest energy, and we haven't been able to show that it goes all the way to ion at the end. Okay, so very briefly, we are undergoing an upgrade at the Pierre Observatory. And this upgrade is mostly based on trying to detect muons, because muons are surviving further in the atmosphere. And so if we measure muons, we have a handle also on composition. And in order to do that, it's actually quite complicated, but we're adding a detector. Actually, we're adding 2 types of detector that are going to allow us to disentangle the muons from the electrons in the shower, the shower that hits the ground. And in doing so, we get another handle on composition, which is really, the part that is really the most interesting and the most important in understanding what the ultra energy cosmic ray spectrum looks like. Okay, so I'm behind. So let me give you very briefly the rationale to go to space, and then maybe I'll stop and I'll take some question, and then if you want to know about space, I'll show you a few slides about that. So this is basically the latest spectrum with the number of events that have been detected at all those energies. And you see that when you go above about 60 eeV, which is where we expect to be able to do charged particle astronomy, so this is where you'd hope to be able to do some kind of charged particle astronomy there. Well, you see, after 15 years of operation, we only have detected about 200 events. Right? It's not very much, and the reason for this is that the steepening of the spectrum is actually much steeper than expected. Right? So at the end of the day, we didn't detect as many as we wanted, and because they are tending to be heavier, the signal is not, it's not sticking out the way we were hoping it would be. So how do we do better? Well, one of the things that we can do is try to go to space, and here is the whole rationale about going to space. You see, the Pierre Auger Observatory, like I said, is about the size of Rhode Island, right? And the number of events that you're going to detect is directly related to the size of your detector. Now, you can imagine that you can cover the whole United States with surface detector, but that would be a bit expensive. So what you could do instead is put a detector in space that is looking down at the atmosphere. And you see that, for example, if you have a detector at 525 kilometers in altitude, and you have a field of view of about 45 degrees field of view looking just down, right? You're actually going to be able to cover an area that is 150,000 square kilometers. So even if you add the duty factor of about 10% here, you see that immediately your detector is 5 times bigger. Is going to be able to detect 5 times more events than before. So this experiment that we're working on, the project is called POEMA. That's an optical, a UV type detector that works like the fluorescence detector that we talked about here. And if you actually do that, you see that your exposure, you can gain an order of magnitude in exposure compared to what Auger can do. With the benefits of being able to observe both the northern and the southern sky at the same time. So you don't have that problem of trying to understand the northern sky and the southern sky, because of the orbit of having a spacecraft in orbit allows you to observe both. So I'll stop here and I'll take some questions. And if you want to know more, I can tell you why the next step for us is to actually go to near space with balloons. Thank you.
Thank you, Fred. That was excellent. We've had a nice introduction, of course, now to the Pierre Auger project and how to expand it by looking from space for cosmic rays over a larger area. Questions from anybody or discussions you want to initiate? I know we actually had peaked at about the 18 participants. We're down to 9, but.
Well, I think there's a lot of interesting science questions I'd like to ask, but my first one is, what about the social aspects of going to, the Mendoza province and setting up a very large physics experiment there? Do you have any, stories you want to share on that?
Well, I mean, it's the Pierre Auger Observatory is an experiment like no others. I mean, I think we all come from, Olga and Nick, you're also coming from particle physics. I presume I come from nuclear physics. When you do an experiment at an accelerator, you could just go there and you do an experiment. It's in a very controlled environment. When you deploy a detector on such a large area, you basically have, you have a town behind you. When you go and you have meetings there, the town, which are, it's a fairly small town called Malargüe, they're aware that this is going on. They know that the scientists are in town. When we have meetings, there is a parade there, and the scientists are basically going through the parade. And this is the only place, I think, in the world when scientists can be considered as a rock star. It has a huge impact on the cultural aspect for the town. There are not many, I think there is only maybe 2 or 3 planetarium in Argentina, one in Buenos Aires, obviously, but Malagüe's got its own, because basically they can define themselves as, you know, a scientific, you know, town, the scientific capital of Argentina. And so this is something, this is like I say, it's an experiment like no others. We, at the headquarters for the experiment, we also have a visitor center. So you know, there are interaction with the public. Outreach is very, very important to this. And so, yeah, I mean, the social aspect, you know, when you go there, it's really a pleasure because everybody knows that the scientists are in town. Does that answer your question, Olga?
Yeah, it does. Thanks. Yeah, you know, I think it requires goodwill from both sides and effort from both sides. And I think the Auger experiment did this right to, you know, form relations before coming in and, you know, just trying to buy up land or something. And it has to be a cooperative effort that involves the local population. And so I think this is something that Auger recognized and did right from the start.
Yeah, I mean, the town has been incredibly supportive to all the efforts. That's been, you know, going there all the time is a pleasure, really, because you feel so welcome.
Okay, other questions anybody's going to have? We had some of our students on, but they seem to have gone. Okay. Well, like I said, we have time for discussions. We want to talk a little bit. We can hang around and talk or ask questions. I
Maybe
think
stop recording and we can chat informally. All right.
Stop the recording.